for yourself, not for your friends or classmates or whatever or whoever. Okay, I'm sorry. Okay, second lecture of the day. Now, Alzheimer and other types of dementia is already the number 2 cause of death in high-income countries. And Taiwan is a high-income country. Okay, so this graph tells us women are more likely suffer from dementia than men. But that is really very unfortunate. Okay, and insomnia is associated with the increased risk of dementia. Okay, so please sleep well. Okay, like, don't sacrifice your sleep for anything. All right. Okay, and dementia is really a serious problem. To demonstrate that, let's look at this table. Let's say a woman in age, her age is around 60 to 64. Originally, we expect if everything go well, she expected to live another 25.7 years. But if this woman unfortunately have dementia, then her life expectancy reduced from this to this, 9.4. All right. So when doctor declared that, Dr. Yan, you are a patient of dementia, it actually issued me an death warrant. You are going to die in 10 years. Okay, that's a death sentence, most certainly. All right, most certainly. But actually, I would disappear less than 10 years because of dementia. After a while, long before my death, I already don't know who I am. I already don't know where I am. I probably won't recognize my wife. And my sons will become total strangers to me. That's not life. So dementia is really horrible, okay? And if my family decided to put me in some medical centers so that those people, they pay them the money, let those people to take care of me. Most likely, I have a 45% of chance to be mistreated, all right? Because these dementia patients can be very, very annoying. Okay, they don't even know how to go to bathroom. Okay, and you cannot teach them how to do that because their brains just don't function properly. Now, there is no treatment for dementia. Why is developing treatments or drugs for dementia so difficult? The first thing is, of course, we are dealing with the brain, which is so complex to model, to understand. The second thing is, even we develop something that we think it is promising and useful, we don't know how to evaluate its influence, at least in a very short time. But if we can use feedback control methods, probably we can have a breakthrough. Why? Because there is one thing in our sleep, which is called REM sleep. Our sleep actually can be divided into deep sleep and I forget the term, okay? Let's just say regular sleep, okay? Stage 1, stage 2 sleep, and deep sleep. And the other stage is REM sleep, okay? During REM sleep, most likely we are dreaming, all right? So REM sleep is a very, very, very interesting part and essential part of our sleep, okay? REM sleep typically compromise about 4th to 5th of our overall sleep time. So last night, 20 to 25% of your time, you were actually dreaming, okay? You will probably tell me that's not true. That's not true. It is true because every normal person has that kind of numbers. The reason why you don't think that it's true is after dreaming, you forget everything. Why? Because your brain don't think the contents of your dreams are important. So they just erase them. It's the dreaming process itself that matters, not the contents of dreaming. Okay, it's the process, not the what you actually the contents of those dreams, because those just not reality. All right. Now, one very important parameter about REM sleep is what we call REM latency. What is REM latency? Is the time between the instant we fall asleep and the instant we have our first episode of REM sleep. This is what we call REM latency. And for Alzheimer patients, this latency is much longer than ordinary healthy people. Okay? So if we develop a treatment and we observe and use that treatment or that medicine to a patient, and if we can come up with sensors to detect its REM sleep and to determine its REM latency, and we have a very good way to determine if this treatment is effective for this Alzheimer patient. Because if the treatment works, this latency should become smaller and smaller, shorter and shorter. Now, by contrast, depression also, patients, let me put it this way, depression patients also has abnormal REM latency. Their REM latency, on the contrary, is shorter than healthy people. Why? Because depression patients often think too much. Okay, they think too much during the day. They think too much during the sleep. So when they fall asleep, the brain jump directly into REM sleep, go to their dream to think again. All right. So, but if I apply the right treatment, behavior treatment or meditation or whatever effective treatment, this REM latency should become longer and longer until it returns to the nominal normal value. Okay, and this becomes a very good measure for how that can help us to monitor the progress of depression treatment. Okay, the point I want to make is that closed loop feedback is everywhere. By applying closed loop feedback appropriately, by using feedback to replace open loop control, we can make many things better, including medical treatments. All right. Now, another thing is biofeedback. What is biofeedback? Let's say I have blood pressure is always my problem. And blood pressure is a risk factor for many diseases, including stroke, including myocardial infarction, which are all very deadly. All right. So I need to regularly lower down my blood pressure. Okay. But I don't want to take too much drugs, too much medicines, because medicines are chemicals. And I think they have their own side effects. But then I was told, if I slow my breath, if I reduce the frequency of my breathing, okay, let's say normally I breathe, let's say 15 to 20 per minute. Now let's change my breathing pattern from natural pattern to slow pattern. Okay, which means I breathe every 10 seconds. I change my breathing cycle from 5-second period to 10-second period. Okay, and I hope my blood pressure will go down. What I can do is let's say I have a sensor to monitor my blood pressure, and I can show my blood pressure how it varies with time. And during that period of time, of course, I will try to reduce the tempo of my breathing. All right? And if I can visually see my blood pressure is coming down and coming down, and it's not just that I have more confidence on the benefit of slow breathing, I will probably, again, try to change the tempo, okay? Is 10-second period the optimal? How about 10.5? How about 9.9? How about the depth of my breath? Deeper or shallower? What are the impacts? And by visually inspect the outcomes, the consequence, then I probably know how to adapt, change my breathing patterns for the optimal outcome, which is reduce my blood pressure, lower and lower. Okay, and if this technique applied properly, this biofeedback method can be applied properly, it actually can improve our health. Okay. Now, recommended session is also a feedback session. Nowadays, when you go to YouTube, when you go to Netflix, you'll see many recommended different people will see different films posted on your computer or mobile phone screen. All right, it's a feedback session. Where does the feedback come from? The information that come from what you have observed, what you have watched on those medias. Okay, it's not just what you watched. It also has something to do your viewing patterns. What will you increase the speed to, let's say, 1.5 or 1.25 of the original speed? When you're watching a movie, where you jump from section to section, or just watch continuously without any stop, okay? That's the viewing habit. Based on what you have watched, based on your viewing habits, based on the location of the device, the locations, your location, based on the devices you use to watch those tapes of movies or whatever programs, okay, they determine what to recommend. So recommended session is also a feedback control system because it alters its offers based on the output, your output, okay, based on your output. Now I want to draw a conclusion to the first part, to the introduction part of this course, okay? Now, I want to talk about what we should learn in college and extend that idea to what we should learn in this course. And this is a very distinguished scholar, He was the president of Yale University from 1993 to 2017. So he was the president of Yale University for 20 years. So he is a very highly respected educator, okay? And he said, if a student graduate from Yale University, actually has a very professional knowledge and skills. Remember, this is the biggest failure of Yale. All right? Now, in Taiwan, in our society, people tend to expect university students can learn professional knowledge and skills from their college education. And I agree with Dr. Leonard. This is not right. If we do that, then it's the biggest failure of our university education. Okay? But if we don't learn professional knowledge and skills from university, what do we learn? Okay? And where do professional knowledge and skills come from? Okay? Dr. Levin have answers for all those questions. Professional knowledge and skills is the students according to their own will after graduating from college to learn a master of things. Okay, does this look abstract to you? Let me try to explain this concept. Let's say let's look at three mechanical engineering related industry: steel industry, auto industry, machine tool industry. Okay, all are giant industry globally. Okay, and these three industries are very important in Taiwan. If we develop 4-year college education entirely on tell you how to make a car, would that be sufficient? I'm not sure. Can I do that to machine tool industry? If I develop all your 4 if we develop all our 4-year college education only to machine tool industry, can I learn everything about machine tool? Probably not, because there are so many different machine tools. And another important thing is even we spend 4 years learning nothing but machine tools, when I go to the machine tool industry. Especially when you graduate, the trend of industry might change. Machine tools will probably become less important, will probably therefore they don't need any new engineers. Okay? So but those big industries are all intensively mechanical engineering related. They don't need students from they don't need many students for computer science or electrical engineers. The majority of the engineers they need should be graduated from mechanical engineering. But we cannot fulfill all those needs. What we can do is teach you the common ground of those big 3 industries. And after you graduate and you decide, I will go to the auto industry or machine tool industry, steel industry, I will simply go to the medicine industry, smart medicine industry. It's your choice. And based on what you have learned in the college, then adapt what you learn from the college to those industries. Okay, this is, I believe, what Dr. Levin tried to say. But if that's the case, what do we learn in college? The core of undergraduate education is to develop students' ability to think independently and to lay a foundation of lifelong learning. So the key word here is, first, independent thinking. Second, lifelong learning. You have a responsibility of learning by yourself, because no teacher can teach you forever. Okay? the most our teachers can do is lay a foundation for your learning. Okay, the next is all up to you. Nowadays, things are getting better because if you know how to use AI, and in particular, large language models, lifelong learning become much easier. It's like a good TA, teaching assistant, of good teachers. And the LLM, such an AI tool, is always very knowledgeable and always very patient. And it will always on duty whenever you need it. All right? Okay. Now, these are references for this course, including these three very good control engineering textbooks. All right? But I think the year of textbooks is diminishing, okay? Is probably has already gone, okay? Because pretty much you can get all the learning materials you need from large language model, okay? I'm not saying you should trust AI 100%. I'm saying if you ask the right questions, he will provide, the AI will provide you sufficient information to help you to learn, okay? Now, please learn how to master the use of those those AI tools, okay? Now, these engineering mathematical books are also references of this course. All right, that's the first part of this course. Let's now switch to the second part. Okay. Oh, I'm sorry. This is not right. Now we will start to dive directly into the control. All right. Now, here for this part, we will introduce you in linear systems and Laplace transform. Okay. Now, before doing that, before tell you what are the definition of linear system, let me introduce you some useful signal models. When I say useful, I mean these signals are constantly used in the process of controller design. All right. Now, the first signal is unit step function. Okay, and its definition is given here. And the behavior of unit step function is actually very straightforward. Its value can only be 0 or 1, depends on its independent variable, which is t. T is often referred to the time variable. Okay, and everybody know what time is. Okay, now the critical point is t equal to 0, because when t is larger or equal to 0, the value of the state function is 1. Otherwise, the value of the state function is 0, right? Very easy. Now, if you multiply unit state function with any function, let's say exponential function, then this is what you will get. You only have values after t equal to 0. Okay, originally this function, this signal of e to minus at should look like this. But after multiplying the unit step function, this part just disappeared. All right. Here comes a very important question. Why is the equality sign here, not here? Does it make any difference? Mathematically, of course, they are different, but which one makes more sense when it comes to the real physical? Why do we choose the equality signs here? Okay, now to answer that question, there is one thing we need to know. What does t stands for? The origin of time. What does it stand for? In engineering practice, there are two different types of specification. The first specification is T equal to Z, stands for the present, right this very instance. As a result, T larger than 0 represent the future. By contrast, T smaller than 0 refer to the past, to the history. Make a lot of sense. Present, past, future. But for control system development, T equal to 0 means another thing. It represents, remember, I will actually said it in the previous lecture. It represents the starting point of control operation. The very time instant you turn on your machine, okay? The very time instant, let's say you ignite your vehicle, all right? No matter in any event, T equal to 0, in this case, represent the time, the very time instant that the control system start to operate, all right? Now, why put equality sign here? Because when you start operate the system, that means at that very time instant, you apply input to the system. Because before operating the system is not subject to any input. All right? When you start the system, you apply input. Okay, so what does the impact of the input stops? Of course, at the T equal to 0. All right, the very instant we stop the operation of the control system. Okay, so remember that. There is a reason we choose the equality sign here, not here. All right, that's the definition of the unit step function. Now, the second useful signal for control system development is what we call impulse function. How do we define impulse function? Okay, let's say I have this function here, which essentially is a rectangular. At least the shape looks like a rectangular. All right. Now, the duration is the value of this function is 1 over epsilon L, 1 over epsilon, when t is between minus 2 epsilon to positive epsilon over 2, right? Okay. Okay. When you make epsilon small and smaller and smaller and eventually approach 0, then this function is what we call impulse function. All right? Now, impulse function has two very important properties. The first is that its value is always 0, except at this very time instant, t equal to 0. Okay, other than that point, in all the remaining values, all the remaining t values, delta t, the value of delta t is always 0. However, if you integrate the impulse function for t equal to minus to t equal to infinity large, then the result of this integral has to be 1. Why? Because we all know the meaning of the integral is the area under the curve of the integrand. Okay, what is the integrand here? The integrand is this function, and this function, by definition, is a function of unit area, because the area of this rectangular, of course, is a product of the height and base. And the height is 1 over epsilon, and the base is epsilon. So the area is 1. That is the reason why the value of this integral is 1. piece of cake. Okay, no big deal. All right. Now, another mathematical property we should pay attention to is this so-called sampling property. That is, if you multiply any function, whatever function, okay, let's just denote that function as g of t, you multiply it to delta of t minus a, then what you will get is the value of g at this very point of t equal to a, okay? Why is that the case? Easy, because for this function, when t is equal to a, then t minus a is 0, right? So when you integrate it, the only thing will happen, the only place this integral will have non-zero value is occur as t equal to a. And the resulting value for this integral is therefore g of a, okay? I don't want to prove it mathematically, okay? But I think it should not be difficult to understand why is that the case. Now, step function, why is that important? Because it represents a constant input signal, right? I have an input which is constant, but that input only exists after the operation of the control system, right? Now, why do I need such a function? Why do I need such a function? The impulse function represents an idealized instantaneous signal with infinite amplitude and zero duration. That which is used to characterize system behavior. What does that mean? Let's say you have a tree, and that tree was struck by lightning. Okay, how large is the force caused by the lightning? No idea, right? How large is the striking force? I have absolutely no idea, and I don't know how to measure it. But one thing I do know is that impact force is very, very large. Okay? Now, again, come back to the lightning struck. How long, what is the time of duration of that lightning struck? I have absolutely no idea, and I don't know how to measure it. But one thing I do know is that that time period is very, very short. So if I want to know what will happen, or what will happen to that tree if that tree is subject to the lightning struck, then the lightning struck itself will be represented by an impulse function, right? Of course, the impact force is not really infinitely large, and the time of duration is not infinitely small or approach to zero. But we know the lightning struck force is huge, and the time of duration of that shock is very, very, very short. So represent that force by an impulse function is actually a very good mathematical approximation, okay? And that happens all the time. For example, if you strike something with a bat or with a hammer, then the impact force can be modeled by impulse function, okay? Because you know the force is very large and the time duration of the impact is very, very short, all right? That is why impulse function is very important. It is so important, actually, you can buy something which we call an impact hammer, okay? And you use it to generate impact force to your mechanical device. Why do you want to do that? Because you want to identify the dynamics of those mechanical devices, okay? These hammers are actually commercially available, and people use them all the time, okay? And what it generates is actually impulse force, okay? Why impulse force is so important? That not just because many force in reality, in nature, can be modeled by impulse function. That is just one important requirement Okay, that is just one point. The other thing is by applying impulse function to the system and then observing what will happen on the output end of the system, we can learn a lot about the nature, the behavior of system. Okay, so it is actually a very good system identification methods. All right. Now, right now we already have learned only two functions. One is unit step function. The other is impulse function. And there is a connection between them. That is, the derivative of the unit step function is actually the impulse function. Why is that the case? I think it's not difficult to see that because the unit step function is continuous when t is larger than 0. It is continuous when t is smaller than. But at the t equal to 0, it has a final jump. Okay, its slope is infinitely large. Therefore, the derivative of the unit step function at the t equal to 0 is actually infinitely large. That is the reason why we have these equalities. Okay, and it can go the other way. That is, if I integrate the impulse function, what I will get is this unit step function. Now, whenever we encounter integral, there are two types of integrals: indefinite integral and definite integral. And the difference is, for definite integrals, we have to specify the lower bound and upper bound. All right? Here, the lower bound is always t equal to minus infinity, and the upper bound is t, and tau is a dummy variable of the integration process. Okay, now what is the t? Simple, very straightforward. T is the time. What is the value of the t? It depends, okay, on your requirement. Let's say if you make t equal to -1, and here this is -1, and the result of this integration will be 0 because the value of the unit step function at the t-1 is 0. By contrast, if you choose t equal to 2, then u of 2, of course, is 1. And the result of this integral will be, of course, 1. Okay? So t is the time that you can specify. All right? So let me summarize. The step function is the integral of the impulse function, while the impulse function is the derivative of the step function. Okay, very easy, but also very easy to forget. Okay, don't forget them. All right. Now let me introduce another important mathematical equality for this course. This is something we have learned in the course of calculus. Or at least I sincerely hope that you'll find this equality familiar. Okay. Okay, not a total stranger. Okay, now whatever. Now the point is e to minus ix. I is, of course, the imaginary variable, is equal to cosine x and I sine x. So apparently this is a complex variable because it has the real part and it has imaginary part. All right? Okay. Now, one big question: why do we need to deal with complex variables in the practice of engineering? Why do we need to do that? Why do I ask that question? Because in the real physical world that we can understand, all variables are real value function. All variables are real numbers. Temperature doesn't have a complex power. Velocity doesn't have a complex power. Stress, strain, whatever physical variable you can come up with, they are all real number variables, right? There are no such thing as a physical variable that has real power and imaginary power at the same time. The funny thing is this power is called imaginary power, which somehow implies this power is not real. It's come from your imagination, come from our imagination. And that is actually very true. Okay? Now, the question now is, if every physical variable are real numbers, okay, why do I have to deal with complex numbers in performing engineering analysis? Whatever engineering that deal with, the mathematics is unnecessarily complex. For engineers, there is only one answer for that, is that that complex mathematical technique will pay off in the future. Otherwise, we have no interest in dealing with TDMS, because TDMS, contact blend max, how valuable, I don't care how valuable they are. Okay, it can satisfy your curiosity, it can help you understand the wonderful world of mathematics. Is of no concern for engineers. We engineers only care about the real world. Okay, whenever we accept the complex mathematics, we want to deal with the complex mathematical process. It's because that process, however complex it is, will pay off in the future. Same thing happened here. The reason why we want to deal with this complex function is with such a representation. In the remaining part of this course, you will find you using such a mathematical tool to describe, to design the control process. The process will be greatly simplified by using such a representation. All right? All right. Now let's look at the third signal model, which is e to x t. E is, of course, the exponential function. Now x here is not a real number. It's actually a complex number. Its real power is sigma. Its complex imaginary power is omega. Okay. In this course, please keep in mind, omega always signifies, it always denotes frequency. Okay, I will formally define frequency in the later part of this course, but for the time being, just keep in mind, in this course, omega represents frequency. Okay, here x is equal to sigma plus j omega, and here x star represents the complex conjugate of x. Of course, by definition, x star should be sigma minus j omega, because that's the very definition of complex conjugates. All right? Why are they complex conjugates? Because they have identical real powers, and their complex, their imaginary powers differ by a sign. All right? Now, what is e to st with such a definition? Let's look at it. Okay, e to st is, of course, after using this expression, becomes e to sigma plus j omega t. Now let's take it apart into a product. This is equal to the product of e to sigma t and e to j omega t. And based on this Euler formula, here x, in this case, become omega t. Therefore, based on Euler formula, this can be rewritten as this. All right? Okay, I can go through this process again, but this time, x is now replaced by x star t. Then what I will get is this. Now, by acting them together, what will happen? As you can see, this and this, these two numbers are actually again, just like them, complex conjugates, because they have identical real power and their imaginary powers only differ by sign, all right? So the sum of a pair of complex conjugates is always 2 times of their real power, because by acting them together, their imaginary parts cancel out the other, right? So this is what I will get, all right? So let me make one point very, very clear. In the future, whenever you see this related directly to this, all right? Okay, this is the signal that we want to deal with, because it's a real number mathematical function. It has not any imaginary part, okay? Now, what is this signal, okay? Now, when we observe these signals, it actually consists of 2 parts. The first part is the exponential function. And from this figure, you can see exponential function represent the envelope of this function, all right? And after multiplying cosine omega t, and we all know the value of cosines is between -1 and +1. So it will oscillate because cosine omega t is function of oscillation with a constant period, constant frequency. But it will always oscillate within the range of the envelope. This is upper bound of the envelope. This is lower bound of the envelope, and it will always oscillate inside the envelopes. Okay. Now, the X here has a name. Its name is what we call complex frequency parameters. Okay, and it combines 2 things: the exponential envelope. Please remember, exponential envelope is determined by the real power of S, okay? And the sinusoidal oscillation, which is determined by the imaginary part of X. Now, that is why you should pay attention to S, because now you understand the physical meaning of the real part and the physical meaning of the imaginary part. The real part of X, the real part of the complex frequency, determines its envelope. It determines the overall trend, the overall shape of the response of this signal. And the complex part, which is omega, it determines not the overall trend, but the local oscillation pattern. Okay, how fast is the oscillation is determined by the value of omega. The larger the value omega is, the faster the oscillation. All right, so envelope is determined by the real part, and the imaginary part determines the degree of oscillation. And by using X, I can combine 2 information into 1 parameter, and that simplifies my representation. It will make my mathematical derivation process much, much more concise and elegant. All right? All right. So this exponential function is very important. This exponential function with complex frequency enables concise representation of both transient and oscillatory response in time system, okay? Forming the foundation of Laplace transform method in control series. As you will see that X play a very central part. I mean, the complex frequency parameters plays a very important role in Laplace transform, okay? Now, why do I want to know, why do we introduce step function and impulse function because they represent important text signals, which can help us reveal the properties of the systems that we want to control. Okay, and step function primarily it can help us perform time domain analysis. That is by applying a step function to the input. That is by applying a constant input to the system and observe what will happen. At the output end of the system, we can learn a lot about the property of the system. And impulse function, the same thing. Okay, all right. Let's come back in 10 minutes. 谢谢。